Hello again. In this lecture, we are going to introduce one of the most important formulas in the world of probability, the Bayes rule. People also refer to it as Bayes' theorem or Bayes' law, so we will use all three interchangeably. For starters, take two events, A and B. According to the conditional probability formula, the conditional probability of A given B equals the probability of their intersection over the probability of event B. Using the multiplication rule, we can transform the numerator of this fraction to get the probability of the intersection of A and B equals the conditional probability of getting B given A times the probability of getting A. Therefore, the conditional probability of getting A given B is equal to the following fraction: the conditional probability of getting B given A times the probability of A divided by the probability of B. This equation is known as Bayes' theorem. It is crucial because it allows us to find a relationship between the different conditional probabilities of two events. One of the most prominent examples of using Bayes' rule is in medical research, when trying to find a causal relationship between symptoms. Knowing both conditional probabilities between the two helps us make more reasonable arguments about which one causes the other. For instance, there is certain correlation between patients with back problems and patients wearing glasses. More specifically, 67% of people with spinal problems wear glasses, while only 41% of patients with eyesight issues have back pains. These conditional probabilities suggest that it is much more likely for someone with back problems to wear glasses than the other way around. Even though we cannot find a direct causal link between the two, there exist some arguments to support such claims. For instance, most patients with back pain are either elderly or work a desk job where they remain stationary for long periods. Old age and a lot of time in front of the desktop computer can have a deteriorating effect on an individual's eyesight. However, many healthy and young individuals wear glasses from a young age. In those cases, there is no other underlying factor that would suggest incoming back pains. All right, similarly, we can also apply Bayes' theorem in business. Let's explore this fictional scenario. Your boss wants you to do research about what companies are looking for in recent college graduates: good academic performance or working experience. You go over the resumes of the last 200 people who matched the requirements and got the job they applied for. Out of those candidates, 45% had the relevant experience. In addition, 60% had good grades. Furthermore, we know that out of those 45% who had relevant experience, 50% also performed well academically. To avoid any harsh decisions, we need to compute the conditional probability of the candidate to have relevant experience, provided they had a high GPA. If we use Bayes' theorem, we get that the conditional probability of a candidate performing well academically to have relevant experience is 0.5 times 0.45 over 0.6, or approximately 0.375. Since 0.5 is greater than 0.375, then it is more likely for an experienced candidate to excel academically than for a student with high grades to have the required working pedigree. Thus, candidates who had internships are more likely to also have a high GPA. Therefore, firms are much more likely to get their ideal candidate if they go for somebody who has experience rather than somebody who thrived academically. Well, that explains a lot. Good thing online courses are a completely different category. To wrap this section up, let's briefly go over the odd case of applying Bayes' theorem to independent events. Take these two events, the weather being sunny and your code not working. You can always try and blame it on the sun being too bright, but deep down you know the weather has nothing to do with your code not compiling. Similarly, rain, wind, and snow are seldom affected by how well your algorithm performs. Let's get more specific. Imagine you know the following. The probability of your code working is 0.3, and the likelihood of it being sunny tomorrow is 0.4. Since the two events are independent, The probability of sunshine, provided your code works, is also 0.4. If we plug these values into Bayes' theorem, then we get that the likelihood of your code working in good weather equals 0.4 times 0.3 divided by 0.4, or simply 0.3. This result aligns with our suspicion that the chances of your algorithm performing as intended neither increase nor decrease based on the weather. Good job, everybody. In the next section of the course, we are going to focus on probability distributions. We will introduce the most important ones, talk about their expected values, and how wide their prediction intervals should be. Thanks for watching.